Okay. Thanks, everybody, for your patience. Like benchmarking, the AV for the talk is fixed as long as it's fixed before the talk is supposed to start, right? Just like it doesn't matter how slow the response is as long as it's within your required time parameters. So we're going to talk a little bit about benchmarking and about storage on Kubernetes. Now, I've been doing this Kubernetes thing for a little while, since, I don't know, 08, something like that. And the reason why I got into Kubernetes is because I wanted to put databases on Kubernetes. I've been a database geek for quite a while. I've been doing database automation as a consultant and that sort of thing. And I saw a real opportunity with Kubernetes to provide a platform for database automation. However, not everyone is as optimistic as I am about putting databases and stateful applications on Kubernetes. A lot of people have seen this tweet by Kelsey, which was the start of an argument between the two of us about stateful applications in Kubernetes. And admittedly, he has a point because there are a lot of issues with running stateful applications in Kubernetes, and most of them relate to storage. That is, storage is still hard. We haven't done a lot to make storage less hard on Kubernetes than it was before Kubernetes was around, so we're working on it. Now, one of the things, if you're talking about storage for a cloud, for a large infrastructure, for that sort of thing, you actually have sort of three major problems in this environment. One is management, as in you have admins and that sort of thing who are used to the storage environment from bare metal, et cetera, used to an older set of tools. They're not used to the new tools. The new tools aren't necessarily as complete or as mature as some of the old tools were, although that's arguable. And so that presents a challenge to doing storage and stateful apps in a cloud-native environment. The second thing is setup complexity. Just the difficulty because you have all of the stuff that you used to have to do to make storage physically work, and now you also have to configure this abstraction layer on top in order to let your cloud-native platform access the storage. And then a third question, or a third problem that always comes up is performance, right? Is people do not want to give up performance for that cloud. Now, in terms of setup complexity, we're already trying to address it through one of my favorite projects, which is Rook, right? So Rook is an operator that configures your storage in a Kubernetes environment. And the goal of this is to simplify storage complexity for people doing work on bare metal or more hand-built clouds, et cetera. And made a lot of progress in Rook. There's still a lot of work to do, but it really is a very nice tool. So that's being addressed. I don't really have an answer for the management problems. For anybody here who is already an admin, who is maybe moving their infrastructure to a cloud-native world, my answer is honestly get used to the new tools. Once you are used to them, they are really better than the old tools, but I can't get you over that step of needing to get used to the new tools. And then the third issue is the one that we're going to be talking about today, performance. Now, there's a few reasons why I want to talk about performance. Number one is, how many people here are a system administrator? Yeah. And how many people here are a database administrator? Yeah, I got a few, right? And you guys don't care at all about performance, right? Nobody asks you any questions about performance, do they? Right? Everything is always as fast as it needs to be. No. So admins really care about performance. It's something they spend a lot of time thinking about. And thus, for the new cloud-native platforms, a lot of trade-off is presented in the form of ease of use, ease of manageability versus speed. And that can be a hard trade-off to make if speed is really important to you. And if you're forced to make that trade-off, then that can be a major migration roadblock. You can say, hey, well, we have everything that we need to move our platform to this new cloud-native infrastructure that we built up, but we're worried that it's not going to hold up under peak customer demand. And we don't have a good way to figure that out ahead of time. Now, the other reason why I care about performance is that I've just been doing that forever. I've been a performance and benchmarking geek since my hair was actually all blonde. And I continue to do that because, honestly, from my perspective, because I'm a crazy person, performance and benchmarking is fun. And so I've started doing a lot of it on new cloud-native stuff. So let's talk a little bit about benchmarking, because part of my goal here is I'm going to present some numbers and some of my own findings about benchmarking. But what I really want you to learn here is some of the tools that are out there and some of the methodologies that are out there for you to do your own benchmarking. Because my hardware is not your hardware, and the numbers that I show you aren't necessarily going to apply to your use case, which means you need to do your own testing. And the tools are not actually as hard as you might think they are. So when we're talking about benchmarking, what we're really talking about doing is comparing. So in English, the word benchmark is both a thing that you do in terms of like a benchmarking test, et cetera, and it's a thing of you've set, this is your mark of how fast or how high or whatever you're supposed to be. So when we're talking about benchmarking, we're really talking about comparing, right? We're comparing cloud-native storage to, say, bare metal storage, or we're comparing new release of Kubernetes or Rook or whatever to previous releases, or we're comparing one configuration to another configuration, or most importantly, we're comparing the spec requirements of, for example, how fast a website request needs to be with what we're actually getting. And so we need to benchmark a variety of different kinds of storage. There are a variety of storage options that we have out there, and they're going to benchmark. So your basic storage, right, what everybody's all familiar with is what we call bare metal storage, right? Now this might be bare VM storage, which is more complicated, and I'm not really going to get into that, but in terms of you're using the underlying platform and file system directly and running stuff on that. And then there's a sort of intermediate step on Kubernetes where you can use local storage. Particularly with recent releases of Kubernetes, we have both host path and local persistent volumes options, which are very similar but work differently in subtly different ways, that allow you to basically sort of directly attach storage from the host, which is actually a good option for a bunch of workloads. Like if you have a database that manages all of its own redundancy, then you don't necessarily need the storage layer to be redundant. And local storage might be your better option. And then a third one, which is actually the most common one, and I think people shouldn't be quite so fast to jump to this as their first option, but everybody's running in public cloud, right? Which means network storage, right? And this could be a SAN, this could be EBS, this could be something else, but network storage provided by the platform. And network storage has its own, sort of set of caveats. And then the final one that we're talking about here is what we call cloud-native distributed storage, right? Where you have a distributed storage platform, you host that on Kubernetes and other tools, and then at the same time it supplies storage to your cloud-native environment. And this is a lot of fun because it is a sort of self-contained thing, right? You are using cloud-native tools to deploy a complete stack instead of a partial stack where you're accessing other things. Now, I'm not going to be talking about network storage for this. If you look at my lightning talk from KubeCon Seattle, that one was mostly about network storage because I did all of my testing on AWS. So you can compare the numbers there. You look at my comparisons there. One of the things that I will say is that in a lot of ways as a benchmarker, it's uninteresting because the performance characteristics of EBS itself, if you're testing on AWS, dominate the benchmarks compared to any other platform choices. Now, let's talk a little bit about measuring I/O, right? Because this is what we're talking about in terms of benchmarking storage, right? So we care about I/O. And there's 4 different kinds of I/O activity. Random reads, where you're looking up random blocks and pulling them up. Random writes, where you're writing random blocks per location to disk. Sequential reads, where you're reading a whole bunch of stuff in a row that is at least logically bundled together, whether or not it's physically stored that way. And then sequential writes, where you're writing out very large blocks. And these are all different activities that different kinds of applications do, and so we want to know how they all perform. Now, it happens to be the case that we can generally bundle random reads and random writes together into one workload, because most workloads that do random reads also do random writes and vice versa, and it's fairly easy to measure them together. Whereas sequential reads and sequential writes are often done at different times. And so this is our sort of standard benchmarking setup. And there's two main characteristics that we actually want to measure. One of them is latency, and latency is honestly what we care about the most, which is how long does it take a single request to complete? Because that's usually what your actual spec is, right? You know, a user saves their profile, it has to come back to them, including the entire stack, including the storage, it has to come back to them in 2 seconds or less, right? That might be your spec, right? And so you need to add up all the layers and make sure they don't add up to more than 2 seconds on a 95th percentile, say. And so latency is what you generally care about. And then the secondary thing that you care about is throughput, right? How many requests at once in parallel can we handle? And sometimes these two can be a trade-off. But we need to know how we hold up for both. So we basically have sort of 3 different storage options and 3 different kinds of I/O that we want to measure, and at least 2 different metrics we want to measure across those. It's actually more metrics. So how are we going to do all this? It's a lot of stuff. What just happens that us folks who are in the database industry have spent something on the order of 5 decades worrying about this. So we have a lot of tools to measure all of these things that are already there, that are already reasonably feature complete, that are already actually reasonably easy to use for lightweight benchmark things. So I actually decided to start with 3 what we call micro benchmarks. Because it's a full benchmark that's like TPC or spec or whatever that has a lot of complexity and measures a lot of different kinds of state and a bunch of other things. But if you just want to measure your storage performance, what you really want is what us folks in the performance industry call a micro benchmark, which is a test that does 1 or 2 relatively simple things in order to see how they perform. And so the 3 that I used for this series of tests were Sysbench, PostgreSQL's pgbench, and the CockroachDB workloads. Now, Sysbench was created by the MySQL team in order for them to benchmark stuff. It's now its own separate open source project, has been for years. And it's actually nice because it's measuring more low-level stuff. It does a bunch of system-level tests of CPU performance, memory performance, DB performance, and of course I/O performance. And you can tell it to do specific kinds of I/O. I want to do just random reads. I want to do just sequential writes, that sort of thing. And it is a much more accessible and easy-to-use tool than a sort of deeper kernel-level tool like FIO, which are out there, but they're hard to learn how to use properly. And so I would recommend if you're just doing this for yourself, use Sysbench. It's a lot easier to understand. The second thing is I'm using Postgres pgbench. This is a tool that ships with Postgres, which is a database micro benchmark based on the TCP/B benchmark, retired archival benchmark from the Transaction Processing Council. And it basically has a very simple workload of financial transactions that pretty much measures reads and writes. So random transactional reads and writes. And plus, I can use the database build process for that, which is pretty predictable, as a simulation of how you would do on a general extract, transform, load. In other words, loading bulk data into the database. And the final thing is, the folks on CockroachDB have produced this workloads package that has a ton of great micro benchmarks that are really awesome and very well documented. Like I am really thankful to the CockroachDB team for putting this together because it's honestly nicer to use than almost anything in the benchmark and performance space. One of them is Bank, that's a lot like pgbench in terms of being a simple financial transaction benchmark. Another one is a lightweight version of the TPCC transaction processing benchmark that you hear people publishing official numbers for. And this is a more complex workload that often tends to be lock-bound. Now, both of these are write-heavy because we're measuring I/O. So now there are some things that you want to do when you are going to do micro-benchmarking on your own. One of them is you need to do more than one run. You can't just do one run. Often random factors that you weren't necessarily aware of will affect the performance for a single run. So you want to do a bunch of different runs, 3 runs, 5 runs, 7 runs. You don't have to kill yourself, but more than one, and like average them or throw out outliers or something like that. Second is you want to do long runs. There's a lot of caching and flushing the cache behavior in file systems. There's caching and flushing the behavior in databases that takes place on like a 5-minute or 10-minute cycle. So if you're not running that benchmark for at least 20, 30 minutes an hour, you're not seeing that behavior, which would affect your real-life workloads. Ideally, you want to run it with multiple file and database sizes, although I'll explain why I didn't actually do this in the numbers I'm about to present to you. You want to have multiple connections or multiple threads for just straight I/O, because in any cloud, you're going to have multiple competing resources. And then the last thing is, if you can, use bare metal to do your testing. And the reason why is, if you are doing testing, because a lot of people are like, well, why not just spin this up on a public cloud, right? Because I can deploy instances easily, I can automate the whole thing, right? Well, there's some problems with that. One is you get this problem with public cloud called noisy neighbors, right? Which is one of the most dramatic things that affects your performance. Is not anything you're doing, but what somebody else who is sharing an instance with you is doing. And as a result, if you are benchmarking on public cloud, you need to run dozens of benchmark runs and be prepared to throw out outliers and average the rest and that sort of thing, and tear down and spin up new instances in order to get any kind of a reliable result that actually tells you how your platform is performing. The other thing is that on public cloud, you can't actually necessarily do really large size workloads because that starts to get really expensive. So if you can test on bare metal, particularly if you're planning on eventually running on bare metal, you need to test on bare metal. That's why I tested on bare metal. So let's go ahead and talk about some numbers here. So now let me give you some caveats here. This involves different tests and different databases and different workloads. And these numbers are only comparable for the same test and the same database between different configurations. They're not comparable to each other because, like, for example, you're going to see the bank and the TPCB, the PG bench numbers, and these are not comparable between CockroachDB and Postgres because the workloads are actually not the same. The databases here are minimally tuned. I put in some basic sort of pro forma stuff, advice of the PostgreSQL project and advice of the CockroachDB project, are just some basic things that you do for performance, but not beyond that. And of course, my hardware and my software and the platform I set up and the number of nodes that I have in the configuration are going to be different from what you're actually using. So these are not your numbers. These are examples of numbers that you could derive if you run tests yourself. Now, this is the hardware platform that I had available to me. This is in Red Hat's open source practice office test lab. So we've got a 6-blade cluster. Each of these blades has 20 cores, 128 gigabytes of RAM, 2 SSDs with 200 gigabytes of space each, and a shared network. Now, there's a couple of interesting caveats that this does to my performance. First of all, one of the problems that I have is doing tests for databases that are larger than memory, which is something you usually want to do in order to force a lot more I/O activity and see how workloads that are larger than memory are going to actually perform in reality. The problem is if I only have 200 gigabytes of storage and I have 128 gigabytes of memory, it's very hard to arrange that kind of a test. So the numbers that I'm going to show you don't include that. Later on, I'm actually going to get some bigger SSDs, and on my blog, I'll actually publish a larger than memory test. But you won't see that in the numbers coming up for that reason. The other thing, shared network was supposed to light up here. The other thing is, there's also a problem with having a shared network, which is I'm on the same routers as the rest of the test lab. And so we have some of the same noisy neighbor problems, and we have, you'll see in performance later on, some network bottlenecking that then makes it hard to determine the actual I/O performance because I'm overwhelming the router that's supporting, I think, 64 blades. So some caveats, and you always run into this. But what happens is because we're smaller than memory, we are mostly measuring, the I/O we're measuring is mostly our ability to sync stuff to disk when we need to. That's the I/O we're measuring mostly, rather than raw pushing large numbers of blocks to disk, because most things are going to get cached in memory. And we have the shared network problem. So now, the first one here is we're going to do our bare metal test, or our host file system test, really. Is a better name for it, right? Which is we're running host install. Kubernetes is actually running, but we're not using it. This gives us our reference numbers to beat, right? This is bare metal, and this gives us our reference numbers for what are we comparing to. If you care, this is an XFS LVM setup for the different volumes, and we're just running it that way. So the first thing we're going to do is sysbench, because that's more sort of your straight I/O performance, right? We're going to see what our random reads and random writes are like, sequential reads, sequential writes. So on this hardware, random reads per second, about 10,700 or whatever. Random writes per second, about 7,000. These are reasonably fast SSDs, so we're getting a lot of little random writes. Because we're pulling mostly from memory, because I have this limitation on database size, the sequential writes are really fast. If you have a workload that's much larger than memory, you'll see that number drop by an order of magnitude. But since we're pulling mostly out of cache, we get 22 gigabytes per second, and then we've got this 88 megabytes per second write on block writes. And that is actually the downside of SSDs, which is that effectively all writes are random writes on an SSD. And so you don't necessarily get a big bonus for doing sequential writes. Now, more complicated grid now. We're going to look at the different database benchmarks here, right? So we've got PGBench, and PGBench has three main metrics that I'm going to look at. It actually outputs a lot more. Database load time, again, simulating doing a load of data. Transactions per second, average latency, because again, throughput and latency, right? These are the things we care about, throughput and latency. And then for the other two workloads, we've got throughput and latency, right? Transactions per second, what are 95% latency, so quartiles are. New orders per second, which is what you usually measure for TPCC, classically in the benchmark. So for the hardware, so first of all, for PGBench, we run there. Load time, 404 seconds to load, build the indexes, everything else. We got that as our sort of start. Over 11,000 transactions per second, and an average 2.8 millisecond latency. So this is our initial sort of benchmark of what we're getting off of the underlying file system, with the general idea that we don't really have ways for the cloud native platform to do better than that. We're trying to get as close to that as possible. Now, the reason why I don't have any of the CockroachDB stuff is I've actually never installed CockroachDB off of Kubernetes before. I didn't start using it until it was available in Kubernetes, and the installation process for installing it on top of Kubernetes is much better documented than the bare metal installation process. And I was getting truly terrible numbers on bare metal, which means I was doing something wrong. So I might have that later, but I'm not going to have bare metal numbers for CockroachDB for this. But as you'll see in a moment, that actually ends up not mattering that much. Because the next one we're going to do is the local volumes test, right? And this is where you use host path, or local persistent volumes, for volumes. So I have a directory that exists on every worker node, and that directory has been assigned to be a host path volume for Kubernetes for these containers that I'm running. And basically, it's just local storage we're attaching in the actual database or sysbench containers. Little snippet of my Kubernetes setup there. Setting up host path is really easy. And let me say again, this is an option for real-world workloads, right? You should definitely look at this depending on what your requirements are for things like databases, et cetera, particularly if you can rely on the database platform itself for redundancy. So what we see here is that, as we would expect, local storage performance is almost identical to just doing it on bare metal. The overhead are negligible numbers, less than 1%, in terms of overhead for the platform and that sort of thing. Because really, we're just going through a couple of layers of namespaces in order to access the same storage we were accessing in the first place. And as a result, it's almost identical. And that means that I can actually get my benchmark numbers for CockroachDB as well as the ones for pgbench, right? So we've got our basic numbers for CockroachDB here, which includes 4,700 operations per second. Again, the new orders, so new orders per minute, 1290, and then our latency target numbers. However, there's something going on here. So Postgres throughput dropped a bunch and latency jumped, and these two are related, right? Higher latency means less throughput because we run out of database client connections and have to wait. And that's actually pretty substantial considering that we're just, once again, going through C groups to access our storage. So what is going on here? And so I did a little bit of this. So the thing was, I needed to run the pgbench client on bare metal because that was how I ran the bare metal benchmark test. But in order to run the pgbench client on bare metal, that meant that I went through node port to access Postgres itself. That is, I created a node port service for Postgres in order to access it for pgbench. Well, the thing is, this means I have some extra network hops and some extra lookup time. And on a workload like pgbench that has a lot of little tiny short database commands that write a single 8K block, those network hops and that lookup time actually matter a lot. And so we can see that here in terms of that overhead. Now, our next setup that we're going to do here is Rook storage, right? This is what we really care about is our cloud native storage, right? Because the cloud native storage is awesome, and so we want to know, can we use this? Is performance on it going to be prohibitive, or is it going to be okay? So I set up this 5-node Rook and Ceph cluster, all my worker nodes. Now, because it is a relatively small cluster as far as what Ceph can do, I only set up one level of redundancy, so 2 copies of every object, right? Did some default tweaks from the documentation for performance. And then importantly, for people who are looking at the CockroachDB setup, this is CockroachDB manual install on top of Rook storage, not the CockroachDB operator, which works differently. So first, let's look at sysbench right here. So doing sysbench again for the storage here. And this looks pretty darn good. So random reads, random writes, we're getting about 1/6 less than doing it with local volumes attached, which actually, from my perspective, is amazing in terms of relative, considering what Ceph gives you in terms of manageability. And for that matter, we're doing, random reads are pretty much the same, pulling it out of, sequential reads are pulling it out of cache, and sequential writes get faster, like a lot faster. And I'm like, what's going on with that? And I actually tore it down, and I rebuilt it, and I reran the tests, and I got the same numbers. And what was going on? Well, what sysbench does for sequential writes is it does a sequential write thing of a group of random files, 48 in the case of my particular choice of workload. So 48 files, which are all being sequentially written to in parallel on multiple threads. Well, that is a perfect workload for Ceph. Ceph loves that because it can actually farm out the actual I/O to its multiple nodes. So I actually got a boost in performance on that. So that's what your real-world workload looks like. You could actually get better performance off of Ceph than you do off of bare metal. However, database workloads are a little bit different. Database workloads, we get a little bit slower. It's actually a lot slower, right? So we've got an extra third of our time in terms of the bulk load characteristic. And then about half of the same throughput on pgbench. And the reason why we're getting about half the same throughput is we've about doubled our latency. Now, that extra latency has to do with the network hopping that we're doing for all of these small writes. Now, people who have never dealt with distributed storage before might think that this looks bad. From my perspective, this looks really good. Because if I set up a Ceph cloud, then I have storage on all of my nodes that I can use with stateful sets, and I don't really have to worry about configuring storage on each individual node. So the manageability gain is tremendous. And this performance compared to earlier generations of distributed storage is actually terrific, getting half. So the question then becomes in a real-world workload is it acceptable given your spec, right? Can you afford to double your latency? In some cases, the answer is yes. In some cases, the answer is no. And we get about the same thing off of the CockroachDB workloads, right? So the bank workload, about half the throughput, about double the latency. TBCC, about double the latency, but the same throughput. Well, what's going on with that? Well, the TBCC benchmark is, like I said, can tend to be lock-bound. And in this case, the locking for conflicting transactions completely overshadows any I/O wait time for new orders. And as a result, the actual number of orders we can process are not different, just the latency of those individual orders. So, continue working on this because I care about performance, because I care about hosting databases on cloud-native platforms. I'm going to be looking at getting access to some bare metal platform with a non-shared network so that I can get rid of having network overhead and network latency obscuring storage performance. Maybe try experimenting on with different overlay networks. This cluster was installed using Flannel. I might want to see if Weave or if Calico or if something else actually gives me better performance out of the box. Like I said, adding more disks in order to be able to run other workloads. Figuring out ways to distribute the benchmark workload over CockroachDB better, which is the one thing the workload toolkit doesn't really do out of the box, and of course Ceph tuning. But some conclusions I'd like you to walk away with here is, benchmark your own hardware with simple database benchmarks as a way of testing your performance before you, for example, migrate platforms so that you know what to expect. Local volume performance should be equivalent to bare metal. Rook and Ceph has good throughput, but about double the latency for random writes. And importantly, beware secondary issues that look like I/O performance differences but aren't. Finally, if you go back and you look at my numbers from the lightning talk, which is on video from CNCF, you'll notice comparing the differences here that the differences there are much smaller, and that is because cloud latency effects mask a lot of performance differences. And as a result, you don't actually see them on public cloud. So I think we have time for one or two questions before everybody runs off for lunch. So, questions? Go for it. Do we have a mic for questions? She's got a mic, yeah? Oh, I have a mic? Go ahead and ask your question, I'll just repeat it. Oh, I'm going to need a mic. I can't hear you. Oh, here it is. Got it. There.
Hey, I was wondering if that was Radar's block device, if you did any tuning, and if you given CFFS thought or two, and what you expect of CFFS?
I did a minimal amount, right. I did a minimal amount of tuning. I mean, part of it was I was depending on Rook as an operator, and Rook doesn't necessarily allow you to change that many settings. And so I just did there were some basic settings on setting cache that are recommended out of the instructions, and I did that, and that was it. So there's probably a lot of opportunities to tune this further.
Two questions. One is, do you have something published where we can copy the actual calls you made so that when we replicate your tests, we can a little bit see, okay, this is at least going in the same direction?
Yeah. Not yet, but I will, like within the next couple of weeks after KubeCon. I actually ran into a bug on Kubernetes in the course of doing these benchmarks, which caused me to fall behind in putting all of this together in GitHub repo format. So watch my Twitter feed, or follow me on GitHub, which is also Berkus, and there will be stuff going up in a couple of weeks that will have recommendations on how to do this on your own with sample commands.
And can you say something about storage OS? Or why do you focus on Ceph if Storage OS is being pushed by Red Hat now?
I actually have not used Storage OS. So Happy to test that as an option sometime in the future, along with some of the other things. I'm sure the Portworx people would like me to test their thing, or maybe they wouldn't. But I was starting out with the things. I work for Red Hat, so I'm going to start out with Ceph and Rook because that's what we're invested in. But I'm happy to actually look at testing other platforms depending on how hard they are to install.
Hi. When you're running the sysbench stuff or pgbench, you're running it in a pod inside the Kubernetes cluster, or you're running it from outside of the cluster system?
Well, sysbench is actually easy because I can actually. So here's by the way, here's the server cluster. And the nice thing about sysbench is I can actually run that in the container. Which means I don't have to worry about network hops, and that's one of the reasons why there was such a minor difference on sysbench and a much more substantial difference on Postgres, is because there were no network hops, because the container had the storage attached, and I ran sysbench directly against the storage. So, let's see if I actually still have sysbench open. Oh. I apparently don't still have a network connection, so I can't actually show you that, sorry. But I was running it in the container.
Hey, I'm probably confused about one part of your presentation, so forgive me if it is just a confusion.
Yeah.
So you compared CockroachDB to Postgres, and CockroachDB actually has built-in replication and all that, and you said at some point they just do 2 replicas using Ceph, but CockroachDB can do its own replication, so wouldn't it be just much more easier to benchmark CockroachDB just running on local volumes and not against Ceph, number one?
Well, but
question?
I did benchmark CockroachDB running on local volumes.
Oh, so the Ceph was not involved when you did CockroachDB at all?
Well, I did both. I did CockroachDB in local volumes, and then I did CockroachDB running on top of Ceph.
Oh,
so I did both of those.
In that case, when you showed a performance number of like 150% drop, it might be that it is actually doing 4 replicas instead of 3 or 2 or maybe 5.
No, we have double redundancy there, right? You have CockroachDB replicating everything, and you have Ceph replicating everything. Like I said, my goal here was to test Ceph, not to test CockroachDB.
Oh, okay, makes sense. So Postgres wasn't only making a normal replica, it would write to a local thing, and then Ceph would do the replica.
Yeah, I mean, the thing is, if I was doing Postgres with replication, it would be asynchronous replication, which would have a negligible effect on performance, so I didn't bother setting it up.
Okay, that makes sense. Thank you.
Yep.
So coming back to running the test inside or outside, shouldn't it be possible to run pgbench inside the cluster as well?
Yes. Here's the problem with that, though, because I actually did do that. The problem is you then have limitations on the amount of CPU and memory that pgbench itself can use on the client side, which affect your results. So I could have done it the other way around, where I actually ran pgbench inside Kubernetes against bare metal storage in order to get a comparable thing. But I'm saying whether or not the pgbench client is inside a Kubernetes pod makes a difference in terms of the amount of throughput that client can deliver. Because you have to actually put memory and CPU limits on it. They're going to be slightly lower than what's available on a bare metal machine, even if it's like 80% of what's available on a bare metal machine.
So should there be any performance difference between a host path volume and a local persistent volume, or should they be expected to be the same?
No, host volumes and local persistent volumes are the same thing. Where they're different is the management of them in terms of creating and destroying them.
Thanks.
But the actual storage attachment mechanism is the same code. Okay, well, thank you very much.